boring rank and border one.
Thank you for coming and thanks for the invitation. So I'll be talking about Waring rank and border Waring rank in this talk, and it will be very, very basic. I promise that. So if you understand basic algebra, you should be able to follow me throughout. So two spoilers, and one is there is almost no connection to proof complexity. Sorry about that. And second spoiler, which is more important, that 20% of my slides are already covered by Anamaya, Marcus, and Prerna. So thanks to that. But I will probably repeat just to remind you some basic stuff, but I'll go through them quickly so that we are on the same page. So yeah, so this is a joint work with Fulvio, who is in Netherlands, Christian, who is in Warwick, Gora, who is in MPI, and Vladimir, who is at Copenhagen. Okay, so the basic idea is as follows. I'll sort of very quickly go through the algebraic complexity, and then I'll define Waring rank and border Waring rank and talk about some of the results that we get, and then I'll conclude. And there is a very thin layer of connection, and then probably one slide that I'll be talking about algebraic natural proof to connect something about Waring rank and border Waring rank, but that's it. Okay, so yeah, as Prerna also started that we want to basically tackle P not equal to NP, and so the point is this proof does not work, and because n is not 1. I mean, this kind of stupid proof does not work. But the point is that instead of this intellectual proof barriers, there are actual proof barriers, that why natural proofs, whatever you can come naturally, why this does not work, right? And that is basically the famous result by Rajborough-Rudich, where they showed that sort of, I mean, they came up with what we can call natural proofs, and they said that most of the lower bound results are basically natural, and they basically don't work to prove P not equal to NP. And to tackle that, so very few techniques are actually known that could potentially break, and one of them was introduced basically by this paper, by Mulmul and Soni, where they published in 2001, which is called the GCT1, where they say that, okay, so this algebraic P not equal to NP, which we can also talk about, which is VP not equal to VNP. There you can actually talk about, so you can set up questions in more algebraically or more, let's say, geometrically, and you can try to attack that question, and that potentially break the natural proof barrier by symmetric characterization. I'll not get into exactly what I mean by symmetric characterization, but I can actually tell you. And so one quick thing. So let's say I have a matrix X, and I take a transpose, and also, sorry, I take X and take A and B such that determinant of A times B is 1. So X is a matrix. So all the, you can say that all the polynomials F such that if, so let's say sigma 1, this is a sigma 1 map, this is a sigma 2 map, all the maps such that basically F is sort of invariant is the only determinant polynomial up to some constant. So these are sort of symmetries of, this is basically the group. You can define the group, and so you can say that, okay, these are the symmetries of determinant. And similarly, you can do something not that exactly the same, but close to that for permanent as well. Now, why this characterization is important? Because for most of the polynomials, this does not hold. So in other words, I can put this and say that determinant and permanent, as Prerna was saying, I'll also define explicitly determinant permanent, but determinant versus permanent, this question, so determinant and permanent, these are two polynomials. They have nice symmetries, but most of the polynomials don't have nice symmetries. So maybe there is a way to actually separate determinant versus permanent, which is not natural, because that sort of breaks the natural proof barrier. So that's why they actually concentrated on this GCT. And how do you find the symmetries and so on? And that's why they said, okay, we study sort of the more geometric problems like determinant permanent, and we try to find some representation theoretic properties of these two polynomials, which is more geometric, but I guess you understand what I'm trying to say. These are two polynomials where we want to separate them by understanding some properties which most of the polynomials don't have. So probably this already breaks the natural proof barrier. Now in this paper, Mulmule and Sohoni defined more geometrically, but you can also independently. So Peter Burgisser in 2001, almost in the same year, defined sort of the similar thing more algebraically, and we'll see sort of the algebraic definitions in this talk, but they are sort of the same. So we can also talk about the algebraic definitions of this. So the point is I'll talk about border complexity in the algebraic setting just via the lens of Waring rank and border Waring rank that I'll define in the coming slides, but that's what I'm going to do. As I said, I'll talk about the algebraic notion, and yeah, so as I said, GCT basically tries to prove lower bounds using these symmetries, which basically you can use representation theory, algebraic geometry, and all kind of mathematics, and probably you can prove that because that is not natural, as I already argued. And what GCT border complexity does is basically it tries to capture a notion of approximation, and we'll also see what kind of approximation we're talking about, because in approximation you can talk about different kind of approximations. Okay. So as I said, the point is to understand border complexity. The point is to understand approximation of certain polynomials. Okay. So here is a quick definition of determinant. We all know what is a determinant. So it's a symbolic determinant is basically you take n cross n matrix. Each entry is a new variable xij, and determinant n is basically an n square variable polynomial, which is the obvious high school definition. You basically expand through rows and columns. You get an n square variate n degree polynomial, which is determinant. And the permanent polynomial is almost the same, but without the signs. Remember, in determinant there's a plus minus. In the permanent there is no minus. All things are plus. These are two polynomials, and these are basically the two polynomials that one tries to understand. And Prerna already talked about VVP not equal to VNP. So this question can be formalized as follows. I have a determinant of m cross m. I want to actually replace each entries by linear polynomials in the variables, and I want to see whether I can write permanent as that. And the claim is I can, but then m has to be super polynomial. There is no way I can do it in a polynomial size. Okay. So this is equivalent to basically the VNP not in VVP question. So let's see what are the kind of bounds we know. This is sort of the bound we know. We know that m has to be like n square, which is by Mignon and Rezer, and Bruno Grene actually proved into very recently, meaning 9 years back, that m is upper bounded by something like 2 to the n minus 1. That's basically the really. Okay, so this is the variance conjecture we would like to understand. Now, just to be in the context, again, Prerna talked about this, that in some sense, algebraic classes separations is easier in Boolean than Boolean, because we know that if p/poly is not equal to np/poly, then we know that VVP not equal to VNP, and this is an unconditional result. There is no GRH involved. But if you want to prove it over complex numbers or rational numbers, then you have to assume GRH. So assuming GRH, we know that p/poly not equal to np/poly basically implies VVP not equal to VNP, the variance conjecture. Okay. So the idea is to sort of understand that, okay, maybe we should first try to prove this before I'm aiming for p/poly not equal to np/poly. Okay. And in fact, of course, we sort of believe that these are not same, because if they are, then pH collapses, and we expect that hopefully it does not collapse. So that is where the sort of Boolean versus algebraic connection stands. Now let's try to understand in one slide quickly the natural proof, and then I'll go to the Waring rank versus border Waring rank definitions. So as I said, we want to understand, we want to prove a lower bound, good enough lower bound for models, circuits or models, and etc. And one thing is to actually come up with algebraic natural proofs. as Marcus talked about this, and Anamai also talked about this. So these are the three properties that we want to come up with. So for n varied d degree polynomials, number of monomials is n plus d juice d. So we want to come up with a polynomial p which is sort of easily constructible, such that if f is in some circuit class Cn and I want to prove, then the coefficient should vanish there, and if p should be easily constructible, that is also the complexity of p should be easy in some sense, whatever the complexity is. And if you want to show something else, so for example, a random polynomial should be hard, right? In that not that class, that sort of implies that if you evaluate at coefficients of g at p, it should be non-zero. Okay, so that is how you sort of set up the lower bound setting in the algebraic natural proof, and the idea is probably to come up with an algebraic natural proof and say that okay, the proofs basically has to be this, and most of the algebraic proofs, lower bound proofs, we know are actually algebraic natural proof to till date. Okay, but now in this talk, we will try to understand this question in terms of sum of powers model, which we called Waring rank, and its approximation. So I'll define this just in the next slide. So we'll try to understand this setting, the same setting for the Waring rank and the border Waring rank. So till now, I hope it's clear to everyone. So, okay. So what is Waring rank? So Waring rank is as follows. If you have a h, which is a homogeneous degree d polynomial, I want to write h as sum of powers of linear forms. What is a linear form? Linear form is basically two definitions. Homogeneous means each monomial has degree d. Okay, so I can take x square y plus xy square because each has degree 3, but I can't take x square y plus xy because this is non-homogeneous, because x square y has degree 3, xy has degree 2. So that is not allowed. Let's talk about only homogeneous polynomials. And what is a linear form? It is of degree exactly 1. So there is no constants allowed. Okay, and I want to write h as sum of powers of linear forms. Now the minimum r that I can write h as sum of powers of linear forms is called the Waring rank. It's sort of a measure on a polynomial. Okay. Now the first question is it defined for all homogeneous polynomials, right? That's the first question we could ask, because, and you can show that for any homogeneous polynomial h, this Waring rank is finite. That means any homogeneous polynomial h can be written as sum of powers of linear forms. Why is the case? This is probably easy to check. If I have representation of f and representation of g, I can trivially have a representation of f plus g, because I have f as sum of powers of linear forms, g also as sum of linear forms, then f plus g trivially has a sum of powers of linear forms. So if f and g has finite Waring rank, then f plus g also has a finite Waring rank. So all we need to prove is that every monomial has a finite Waring rank. And what you can show is that there are trivial, somewhat trivial upper bounds, but this is sort of a type. So you can show that for any monomial x1 to the e dot dot xn to the en, the Waring rank is sort of this, where e1 is basically the minimum. So let's say e1 less than equal to e2 less than equal to en. So you basically drop the minimum one, and other things you can show this is exactly equal to the same. This is what you know. In particular, if you look at e1 equal to e2 equal to en, that means just look at the monomial x1 up to xn. The Waring rank of this is 2 to the n minus 1.
Yeah, so does this also work over all fields, or is it just over complexes?
So this works over complex, or I think large enough. I think you have to talk about more than
using primitive roots.
Yes, something like that. Yes.
Okay. So if over reals it won't work, but you can.
Yes, but over complex.
Okay.
Or real word extension.
Yes.
Okay, so this we know. So for every monomial we know we can do that, and using this we know that for every polynomial we can do that. So Waring rank is finite. Good. So now let's try to look at one example which again I covered, but again let's look at that. So let's say I want to look at Waring rank h equal to 1 bivariate degree 2 polynomials. So bivariate degree two polynomials look like ax square plus bxy plus cy square, right? And suppose it's a square, it's a single square, because Waring rank 1 means it's a single square. Now let's try to understand what is this. So let's say then that means that this is of the form alpha x plus beta y square. And if you expand this, you'll note that the middle thing square minus 4 times this is 0. You observe that. Moreover, you also observe that x square plus bx plus c is basically this. So you can also look at y and y square, then this will be like y, it does not matter. So this is also a perfect square if b square minus 4ac is 0. So this is saying that Waring rank equal to 1 is explicitly the set defined by this equation b square minus 4ac is 0. That also Anamai talked about. Okay. How does this help? You can prove that Waring rank at xy is greater than 1 because xy is what? 0, 1, 0. And 0, 1, 0 is not in the set x1 because 0 square, 1 square minus 4 times 0 is non-zero. So it's a way of proving that xy does not have Waring rank 1. Okay. So you can define these things. But now, as I promised, let's talk about approximations that I promised that we'll talk about approximations, and why we'll talk about approximation is also in geometrically also makes sense because we are talking about equations where a, b, c vanish. So this is sort of a closed set. This is sort of a variety. So it makes sense to talk about the closures. But we'll talk about some different kind of closures or approximations here. So let's try to define that. So as I said, that what kind of approximation are we talking about? Because you can come up with probably many sort of definitions. For example, physicists can say that, oh, this is r and this is r, but whatever, I don't care. Cosmologists can say that, okay, pi is 1, I don't care. Even theoretical computer scientists also say 10 to the 5 is just a constant, it is inside order, I don't care. So it depends on what kind of approximation you are really talking about, right? So the point is, here we will try to understand what kind of approximation we are talking about in terms of Waring rank. Okay, so let's look at this example. X square y. I want to write x square y as sum of 3 cubes because x square y is degree 3. I want to write x square y as degree 3 cube. So I can write it as this. By the way, our field is basically complex. Assume that everything is complex. So it is a sum of 3 cubes, right? Because you can basically include this cube root of 6 or cube root of minus 6 or whatever inside, and these are all fine. So these are sum of 3 cubes. And you can also show that this is exactly 3. That means you cannot write x square y as sum of 2 cubes. It's a very trivial exercise. You can just say that, okay, x square y, if it is of the form something cube plus something cube, there will be a trivial contradiction. So x square y cannot be written as sum of 2 cubes. Okay. Now look at this example. Consider a epsilon which is non-zero. And look at this expression 1 by 3 epsilon times x plus epsilon y cube minus x cube. You basically expand that and you take basically epsilon closer and closer to 0. Take the limit, but never 0. Don't put epsilon equal to 0, but let's sort of take the limit. So you get the polynomial x square y. So what is happening is that whenever you take a very, very small epsilon, let's say epsilon is 0.00001. Then what you can do is you can sort of insert this cube root of 3 epsilon inside x plus epsilon y, right? Because again, this is a small constant, so you can always push this. So h epsilon, in other words, is a sum of 2 cubes whenever epsilon is small, any non-zero constant, right? But the moment epsilon tends to 0, or if you put epsilon equal to, so you cannot put here epsilon equal to 0, but in this expression it makes sense to put epsilon equal to 0. But nonetheless, the limit, which is like x square y, suddenly you have proved that this is 3. So there is a mismatch going on, right? So I'll repeat again. So what is happening is that you have x square y, you can sort of approximate that by sum of 2 cubes, but suddenly at the limit you cannot. So in terms of the whole picture, this is sort of the picture. So let's think about this set as Waring rank less than or equal to 1, this set as Waring rank less than or equal to 2, this set less than or equal to 3, 4. So what does this polynomial set x square y? Note that x square y cannot sit inside this set, and it cannot sit outside this here as well, because if x square y is here, then there should be a sequence that actually comes here in between. So that will make say that h epsilon has Waring rank 3. That cannot happen. So it has to h epsilon has to stay inside this, but h cannot really come here. So it has to be really in the border somehow. Otherwise, there is no point that it appears. So just to be clear out, I have h epsilon approximating x square y. This h epsilon has to be here. H cannot be here because otherwise you have to approximate something by h epsilon here, which is contradict this point. H epsilon less than or equal to 2. So x square y has to sit really in a border. So think of this like in the border, and that's how we define the border Waring rank. So the border Waring rank exactly can be defined as this. So border Waring rank of a polynomial h is basically I want to write sum of powers of linear forms, but Li has epsilon terms like epsilon square and so on. It has also 1 by epsilon and so on. So over epsilon this field, and I want to take the limit, and I want to write it as sum of powers. So the same definition but with the limit, right? So by the definition or by the example that I showed you in this last slide, what border Waring rank of x square y is 2. That's what we sort of showed. And because you can rewrite the same example like this, you can sort of insert this 3 epsilon to the 1 by 3 inside, and this is basically the sum of 2 cube as a limit. Okay. Sorry. Yeah, so 3 epsilon to the 1 by 3. Yeah. So okay, but what you can also do is epsilon to the 1 by 3 you can rename it at, let's say, epsilon prime. That also tends to 0, and then you can also do that. But you want it doesn't matter. So x square y can be written as sum of 2 cubes. So our border Waring rank of this is 2. Now, as I said, now I will not talk about that, but the lower bounds or most of the lower bounds for Waring rank, or the trivial lower bound for Waring rank, is basically via partial derivative equations and so on. They basically, that is basically natural proof, and that will also give lower bound for border Waring rank, because as I already mentioned, this is basically border basically captures all the things that will also vanish at the limit, right? So whatever natural proofs you come up with Waring rank will also hold for border Waring rank, right? So that means we really don't understand Waring rank and border Waring rank in this lens. If you really want to understand Waring rank and border Waring rank from this lens of natural proofs or defining equations, we don't really understand the difference between Waring rank and border Waring rank. So we want to understand Waring rank and border Waring rank. Here is the question: if border Waring rank of a polynomial is k, what can you talk about the Waring rank of this polynomial? It's a natural question, that how large can the gap be? What is known is a d to the k kind of upper bound. So that means if k is like constant, this is still poly d. Okay. And what is also known is that if border Waring rank is less than or equal to 5, then this is like order d. It was so less than or equal to 4. They proved, Landsberger and Tytler proved in 2010, and then 9 years later, Valjo proved that for equal to 5, what happens? But from 6 and so on, we did not know before our work. But in this work, we show that when border Waring rank is k, then we show that Waring rank is less than or equal to 4 to the k times d. Okay. So that means for any constant k, Waring rank is sort of order d. So this basically generalizes this, and of course this is a huge improvement of the trivial d to the k, because when k is constant, let's say 100, then this gives only d to the 100 or something, but this gives still order d, although the order is really large. But and sorry, so the proof has something where k is less than d. Yeah, I don't know what happens when k is greater than d, but that is most probably not a very interesting case anyway. We always, and so okay. I mean, it can. For hard polynomials, we know that k is really large. We know that, but yeah, our proof has some technicalities where we can't show it for k greater than t, but k less than equal to d, we can do that. And so even if point k is log d, then Waring rank is poly d. That's what the question, the result is. And but still, this equation, we don't really understand the equations for general k, but still we are able to show some kind of this bound. Yeah. And okay, so this is one result of between Waring rank and border Waring rank, and then I'll conclude by this slide. So there is another interesting connection which was sort of observed by Kumar in 2020. He said that if border Waring rank of a polynomial f is k, then I can always approximate f as a product minus 1. I mean, forget about the constant. It's like a constant multiple. So if you look at epsilon, limit epsilon, take limit epsilon, then basically this is true. But for most of the, yeah, so that implies actually for any f, this kind of thing is possible, because we know that border Waring rank or Waring rank is sort of universal for any homogeneous polynomial f. This is finite. So for any polynomial f, we know that we can write this as sort of this alpha times product 1 plus li minus 1 as a limit. It's a very trivial model. So we can always write f as that. And in particular, when border Waring rank is small, this s is also small. This proof is basically showing that. The obvious question is, what's the converse? If I can write f as a limit of this, can I also show that border Waring rank of f is small? That would sort of prove that this is really like a interesting model, but closely connected, right? But that is not really the case, because trivially you can write this monomial in this form. You write epsilon to the n times product minus 1, and you can compute, and you can say that x1 up to xn is also in the model as a limit. Note, x1 up to xn has border Waring rank known to be 2 to the n by root n or something like that. So we know the exponential lower bound for border Waring rank for monomial. So trivially, we cannot expect a converse of this, right? So again, just to be clear what I'm saying, I know that if border Waring rank is small, I can write this as a product minus 1 up to some multiple as a limit. And I want to sort of show a converse, that how powerful is this model is. I know even monomials can be computed in this model, which has border Waring rank large. The question is, what else can it compute? As I said, border Waring rank is exponential n. We actually, in the same paper, we show that these are sort of the only case that is possible, in the sense that if f is indeed a limit of this model, then either we are in this case border Waring rank, or we are actually in this case, but instead of x1 up to xn, we have L1 up to Ln linear polynomials. Note that you can always write L1 up to Ln also in this form, because xi instead of xi it will be Li. So this is trivial in this form. So these are the only two sort of possibilities in this model. So previously, last year or 2 years back, with Nitin and Pratik, we showed that a much more general result, but we only showed that these are sort of a small ABP, but this is much more strong result for this specific model. And we also generalize this, instead of Li, we can sort of look at, let's say, 2 cross 2 or 3 cross 3 matrices. So think of one as identity, Li, instead of Li, you have matrices, 2 cross 2 matrices or 3 cross 3 matrices of linear polynomials, and you can sort of look at this model of the limits, and you can study. And it turns out that this kind of model is already very intimately connected with the let's say proofs of so with 3 ABPs, like for example, with 3 ABPs we know are sort of complete, in the sense that VF is BBP3. We know that any with 3 ABP is as powerful as formulas. So this kind of proofs also can be interpreted in this model that we show. We are not going to go into that, but all I'm trying to say is even this model is very powerful if we talk about limits. It's a very simple product minus 1, but that could give a lot of results. Okay, so I'll conclude. The first question is, obviously, can we show that if border Waring rank is less than equal to k, then Waring rank is also polynomially bounded? what we showed is d times 4 to the k bound, right? Can you show a polynomial upper bound? And the second point is, can we find explicitly the equations? I mean, we sort of know that there exist equations and so on, but can we explicitly find the equations? Or we can say that, okay, here is a equation for border exactly k, but somehow we sort of manipulate that and try to give a gap between worrying rank and border worrying rank. Can we sort of exploit that and show something like that we don't know? And we sort of also have some bit of results in this depth 5 models. So let's say I have sigma with sigma with sigma. That basically means that sum of powers, sum of gi to the d, where each worrying rank also is less than or equal to s, small something. And when you basically bound your top n in here to be constant, we can talk about some border. So we can talk about the strengths of or weaknesses of this model. So what is the class when we allow approximation in this model and so on. Sumanta is actually here in the audience. We have some results with when the top n is constant. So so basically this is like a composition of sum of polynomials. So composition of worrying ranks, you can think of that. So yeah, so that's all I wanted to say. Thank you. Question? So can you say something about, so if you know that your polynomial has border worrying rank k, you know there is an expression involving these epsilons or something. Can you say something about the degree of? No. So yeah, we can't. I mean that was a point that we probably can say about something about the epsilon. I mean locally we can that. I mean the way the proof goes, we can sort of locally say that the epsilon degrees are small. But when you look at the whole proof, so the proof, okay, so the point is that you can think of L1 to the D plus L to the D plus L3 to the D. There's a 3 sums. When you, let's say L1 and L2 has same constant, epsilon 3 constant, and L3 has some different. You can show that L1 to the D plus L to the D. You can group it, and you can say that you can use small epsilon like up to K or something, or 2, for example. And for L3, I can also show something, but when you combine, it's not clear. It makes sense. So there is a very localized proof. We sort of say that whenever it's like a more like a Hensel lifting. Like once the constant terms are same, we can sort of group them and prove limits. And for that, we can prove epsilon power like k minus 1, k something like that. But when it's globally, we cannot. At least we could not from this proof. Yes. But yeah, if you can prove epsilon to be like that, then it's a trivial. You can interpolate and prove that, okay, I mean the worrying is small or something. Okay, tomorrow.